From time to time, we all suffer from musculoskeletal problem. Right now, you might be sitting there with one, and you might be going, oh, my hip's very, very sore. Okay, this might be because due to a sporting injury, or it might just be the sheer aches and pains of hunching your shoulders over when studying, or it might just be the sheer aches and pains of getting old. So, in our society, we are an aging population. And we also have many technological advancements, which makes musculoskeletal conditions one of the major health issues of today. So how do we test these musculoskeletal conditions? Well, either we use in vivo methods, which are experiments performed in the body, or we use in vitro methods, which are performed on knee joints or spinal segments, and they're often done in a robotic simulator. Or we use computational models, which are programs that create virtual models. So today my presentation is going to revolve around the in vitro method. So these in vitro methods are really based on the capabilities of the robotic simulators. So if you have a robotic simulator which is able to simulate many different types of tests for various joints, we will be able to increase the musculoskeletal research performed in those machines. So Flinders are lucky enough to have a novel Stewart platform that's supposed to be moving, which is simulated via these 6 legs that extend and retract to form 3D motion. So over here we can see the 6 degrees of freedom. 1 degree of freedom being translation or rotation around a certain axis. So altogether, that's 6 degrees of freedom. It's also important to note that we place the specimen inside the inner space just here, which is shown by a blue foam. So how cool would it be though if we could test all sorts of joints in this robot? So at this stage, this robot can only extend to 25 degrees and also flex to 25 degrees. If we're able to test all sorts of joints in this robot, then we can increase the depth of biomechanical research done at Flinders University. So the idea behind this is a baby cradle. So what does a baby cradle do? Well, it just swings like this. So we can mimic this by flexing and extending. So the cradle flexes and extends to form that motion that we want. We want to place this cradle inside the inner space of the Hexapod just there. So how did I do this? Well, I broke it up into 3 different parts. The first part being analysing the geometric constraints. Really, the space in there is quite tight. We only have 380 millimeters, which is roughly that big, and in height 455, which is roughly that big. So it's actually really hard because we need to analyse the kinematics of this geometry as well as identify any collision points. Second, we need to make sure that the cradle is able to withstand the static loads that might undergo during testing. Third, we also need to be able to simulate the dynamic motions that are going to occur while testing. So I'm going to go through each stage. So first, we can see here that the encoders and the cradle are quite close. And we're going to simulate the cradle motion via Hexapod kinematics, which is based upon the relationship between the bottom encoders and the top encoders. I used 3D vector geometry to relate the cradle to the encoders, which I'll show you coming up. But this is just obviously computational, so I had to validate it via a prototype model. So that's over here. So as you can see, it's quite hard to see because it's acrylic. So while I hope to challenge your brains, I also am going to challenge your eyesight. So this prototype here extends and retracts and forms the geometry determined by the computational model. And there, as you can see, is a knee setup in the model. So here is the model in dynamic motion. The cradle is flexing and extending in kinematic data, and the Hexapod legs are rotating around plus or minus 10 degrees. So from this, we can determine where the distance between the cradle and the encoder, the closest encoder. So basically, all we need to do, all right, is determine the encoders at its end range of motion, as well as the cradle at its end ranges of motion. So I also validated that through, as you can see, it's very hard to see, the cradle, and we drove the cradle to the certain position and measured it. So you've got this way, and then this way. So the most important one though, also noting that the carefully thought out cradle did not collide at any end range of motion. But the most important part was the fact that we increased the range of motion to 140 degrees by flexing the hexapod to 20 degrees while flexing the cradle to 120 degrees, equaling 140 degrees cradle flexion. So as you can see via the computational model, we determined it was 23.4 millimeters. In this model, we also determined it was 23 millimeters, which is a very good correlation. So second, we had to analyze the static stiffnesses that the cradle needs to undergo. These were based off of the specimen, which are roughly around 5,000 Newton meters, as well as the Flinders Hexapod, which ranges from 2,999 to 17,000 Newton per millimeter of stiffness. Stiffness being the ability of a structure to withstand deformation. So, through optimization, an optimization process using FEA, we tuned the cradle stiffness so that it matched the goal stiffness, and we found the stiffness to be 3,251 to 17,300 newtons per millimeter. So thirdly, we just needed to analyze the motor specifications. We need to find a motor capable of simulating this dynamic motion. So in the literature, we found high torques of 218 Newton meters and elbow pitch of 928 degrees per second, which is very, very high and probably unrealistic in a robotic simulator. So by the cradle's structure, as well as figures that would be able to cover the majority of biomechanical tests performed, we were able to distinguish that the torque, the absolute lowest, was 50 Newton meters that we wanted, 60 RPM, and a high accuracy that matched the hexapods, as well as a fatigue, as biomechanical testing is quite repetitive and cyclic. So, but the problem is that we have, motors and gearboxes of 60 Newton meters are quite large. So, there's 300 millimeters here, and as you can recall from before, the hexapod's width was only this big. So it's going to be very hard to fix a normal motor into that space. So through extensive research, I found a harmonic drive actuator. So this actuator had a length of 93.5 millimeters, and it weighed 3.1 kilograms, and it had a torque of 58 Newton meters continuous and 178 Newton meters maximum torque. So you might be wondering, how does this happen? So this happens because of the compact strain wave gear technology that they've used. So it's comprised of three components, this one, and this one. This is a wave generator that has an elliptical shape. So its theory is to move the metal around this circular spline, which then moves this circular spline, and then the teeth move with the teeth of the inner space of this circular one, the back one. Okay, so basically this compact gear is the reason why we are able to have this harmonic drive of 93.5. It also has a 60 RPM of speed, and it also includes no backlash, which means that we have high accuracy. It also includes a brake, so we can do stiffness. We can also perform static and testing. So basically, this is their final design, where we're able to mimic physiological loading and motion for most joints, most joint testing that can be performed, and we are able to increase the range of motion from Hexapod to Hepta-pod while increasing the biomechanical depth of testing that we can do at Flinders University, which will accelerate our understanding of musculoskeletal conditions. Thank you.
Any questions from the judges?
I'd like to be an expert on that, but it sounds very complex. Now, how you sort of, what's the acceptance of this technology in the real world? I mean, hip replacement happens, by millions.
Yeah.
And can we apply that as we speak, or is still being under development? The technology, the principle of, working that out. I mean, technology now evolves a much wider scope of ability to collect data.
Yeah, so obviously we'll have to put the design into practice, and then when tests can be performed in the Heptapod, then we can, those results will be hopefully the